Did we have any questions? Why are there still people yelling? Yes. Yes. We're not going to do Chem 12 AP because you won't like that. Okay, we're going to do a quick little review of a few things we learned last day. So if you were away last day, you can get caught up on it. And if you were here, it will be a nice little review for you. I would like you to tell your partner, or the people near you, where did I put my pen? There it is. Get rid of all of this. What do we call the ones that are shaded in yellow? Tell your partner, what do we call those ones that are shaded in yellow? Okay, so I'm hearing the word group, which is good. So this here is a group. Groups go up and down. So that is group number 1. And other than hydrogen, all of these guys also belong to a group that has a name. It is the alkali. And how do you spell that? It's A-L, alka, ka, K-A, L, li. So those are your alkali metals, yes. Okay, how about all the elements in group 2? What are those called? Those are called the alkaline earth metals. And you don't need to write this down. This is in your notes. And we'll be going over it again today. But alkaline earth metals. I spelled earth with the E-A-R-E. Earth. Sorry about that. Metals. And then we have everybody in the middle. What do we call all the guys that are inside of this red box here? Tell your partner. Those are the transition metals. Okay, now, which groups don't have any particular name? This one, 13 has no particular name. Neither does 14. Neither does 15. And neither does 16. So those ones don't have a name. If you're really into like geeky stuff, the nitrogen group is actually called the pnictogens, spelled with a silent P. How fun is that? And the oxygen group is called the chalcogens, but again, you don't need to know those. I didn't even know them till I started teaching. So you certainly don't need to know them. Group 17, though, has a name. So that would be these ones here, second from the right, group 17. See if you can tell your partner what the name of group 17 is. So you can think that they have a halogen. So those are the halogens. Yeah, you had kind of the right letters going on there. That was good. Okay, so we have the halogens. And then our last group, I'm running out of nice colors. So I think I'm just going to point to it. Or maybe I'll just do like this. This last group here is called the noble gases, yes. So you guys are doing really well so far. Okay, that's awesome. So the groups go up and down. What do we call the things that go side to side? Tell your partner. They are periods. Periods. Yes? How many elements are in period number 1? How many elements in period 1? So if we look at period 1, that's our first row. There's one over here, and there's one over here. So there's 2 elements. How many elements are in row period number 2? There are 2 here, and then another 6 over here, so that's a total of 8. And how about row 3? 8. Do those numbers look familiar to you? The Bohr model. So if you ever forget the maximum number of electrons in the Bohr model, you can always look at your periodic table and say the first shell contains maximum 2. Second shell contains a maximum of 8. And what we're doing when we've got the Bohr models is with hydrogen and helium, we go from hydrogen, which has 1 electron, to helium, which has 2 electrons, and then it's full, and we're finished row number 1. And then we start on row number 2, we start on shell number 2, and we start filling up shell number 2. So everything in the second row is going to have 2 occupied shells. Yes, so we'll go all the way from 1 electron to how many in the second shell? 8. So we'll go all the way from 1 all the way up to 8 electrons in that second shell. And then we'll do the same thing for the third shell. So period 1, we're filling up shell number 1. Period 2, we're filling up shell number 2. And period 3, we're filling up shell number 3. So if you ever see an element and I'm like, well, how many shells should you have? If you are drawing a Bohr model of arsenic, you look at arsenic and you say, okay, I wouldn't ask you to do arsenic because it's past where we're supposed to draw Bohr models. Let's say phosphorus instead. How many shells would you be drawing if you had phosphorus? 3 shells. How many shells would you be drawing if you were drawing calcium? 4 shells. Okay, and then the bottle falls apart after calcium. Okay? Alrighty. While we're here, I'm going to erase some of this mess I've made. Blah. Okay. There is an invisible line on this periodic table, but if you want to draw it in on your periodic table, you may do so. Okay, I actually would recommend on your yellow periodic table that you take your pen and you start right here at the corner, top corner of, who's that there? Boron. And what we're going to do is we're going to draw a bold line down, and then we're going to go across. And then we're going to go down. Guess what next? Across. And then down, and then across. And then down. And what kind of a shape are we drawing here? We're drawing a staircase, yes? And I would like you to think back to what we learned yesterday and think, what is that staircase? Sorry, yes. Yes, the metalloids are right near the staircase, but if we want to simplify it anymore and just pretend there's no metalloids and there's only metals and nonmetals, that staircase essentially separates the metals from the nonmetals. So, the staircase separates metals from non-metals. Yes? I will show you where the metalloids are, okay? They're essentially the ones that touch the staircase with one exception, okay? Metalloids actually touch the staircase. So we're going to look at things close to the staircase, and we're going to decide if they are or are not metalloids. So metalloids touch. We all clap really loudly. Okay, let's go. I don't know, just because they clapped over there. I used to have a teacher who, she was my mentor. She was my department head at Alpha when I first started teaching there 28 years ago. And she used to teach, we both moved to Mountain together in 2000, and she used to teach right on the other side of this wall. And sometimes, you know, she'd teach on the board a lot because she was taller than I am. I can't teach on the board very much because I can only reach like halfway up. But she would teach on the board a lot. And so she'd be gesturing at the board and she'd be like, tap, tap, tap. And I'd go, bam, bam, bam. And then we'd like play games. Yeah, we had a good time. It was fun. I miss her. But when she was 43, her dad sold his company, which was something to do with like refining oil in Alberta for $300 million. And so she retired. And I'm like, my dad's a physics teacher. This is not going to happen to me, but oh well. Anywho, Yeah, so we have this staircase that separates the metals from the nonmetals, and then metalloids touch the staircase. So let's take a look. Who touches the staircase? There is one exception, and I'm going to tell you what it is, and you'll remember it because you'll just know it. Which elements touch the staircase? Boron. Boron touches the staircase. Okay, so I'm going to shade that in. You can get a highlighter or you can just shade it lightly with pencil. Who else touches the staircase? Silicon. Who else? Now, that aluminum is the one exception. Aluminum touches the staircase, but if I ask you to imagine aluminum foil, I'm going to go get some aluminum foil. Talk about apparently 10% of the population does not have visual imagery when they think of something, which shocked the heck out of me. But then again, about 5 years ago, I also found out that a certain portion of the population, when they're thinking things, they think in concepts and ideas and things like that, but they don't think in words. And if you think in words, you're probably like, what? People don't think in words? Because that's what I was like. I'm like, what? People don't think in words? But no, and they're perfectly capable of doing everything. Like, it's just if they were writing an essay, they wouldn't think the words and then put them on paper. They would think the ideas and then the words would come. I don't know how it works because my brain is like words and images. And I watched this artist who doesn't have visual images inside her head, and yet I watched her draw these things that were incredible. And I think about my own drawing, which is like stick figures, and I'm like, how could she do that when she doesn't have a picture in her head? When she thinks of like an apple, she doesn't see an apple, right? But she can draw an apple. So I don't know how it works, but it is really interesting. So if there is anyone in here who doesn't picture things, here's some aluminum. Now, what does aluminum look like? It's shiny. If I had a large piece, it would be hard. Yes? Huh? Well, it doesn't matter. Those bottom ones don't mean anything. Okay? I'll talk about those in a minute. Yeah. So what do you think? What kind of element do you think this is? Is it a nonmetal or is it a metal? It's shiny. It's the only reason it's soft is because it's so thin. But if you actually had a piece of aluminum, like they make patio furniture out of aluminum. Is patio furniture soft? No. They make pots and pans out of aluminum. Are pots and pans soft? No. So aluminum is hard, it's shiny, it conducts electricity, therefore it is a metal. So it is the one element that touches the line that is not a metalloid. Okay? It's the one element that touches the staircase that is not metalloid. Now the good news for you is this: if I were ever to ask you about metalloids, it would probably be a multiple choice question, and I would not put aluminum as one of the answers. because I wouldn't want to trick you, okay? I might put boron, I might put silicon. Who else is a metalloid? Who else is touching the staircase? Arsenic. Who else? Germanium, not geranium. Geranium's a flower. Germanium, like Germany. Germanium. Antimony, which has that funny symbol, SB. And, yes. Yep. But you have to tell me another metalloid first. And remember, metalloids, what do? Metalloids touch the staircase. Tellurium, yes. Okay, and then to be honest with you, this area of the periodic table down at the bottom, you may notice that your periodic table is just missing some elements, yes? Honestly, nobody uses these elements. Okay, this area down here, no, I'm circling too far. Lead is useful, but like these elements down here, la 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 la. Quite frankly, any of those elements down there, no, you're never going to see them in Science 9. So if you don't know whether they are metalloids or, whoa, what happened? If you don't know whether they're metalloids or not, don't worry about it. Yes? I mean, you could go down and you could say, okay, astatine is a metalloid, but the problem with astatine is it's very radioactive. Which means its nucleus will decay and it will turn into a different element. So we cannot get enough sample of astatine to stay around long enough for us to look at it, its properties, and decide, is it metallic, is it non-metallic, or is it like a metalloid? If something only lasts for a second, how could you tell what its properties are? Yes? When we get to the very bottom of the periodic table, elements are radioactive and they tend to fall apart into simpler elements. And so it's really hard to tell what they are. So I'm never going to ask you about astatine or oganesson, whatever the heck that is. Oganesson, which is after radon, right? Oganesson is here. And I mean, technically, I guess you could call it a metalloid, but it doesn't last long enough for us to really know. So don't worry about the very, very bottom right of the periodic table. Is good? Okay. And if you're missing stuff there, it just doesn't matter. Okay? Now, those are our metalloids. Oop, I forgot polonium. However, polonium's far enough down that I won't ask you about it. Okay? Everything to the left of the staircase so that's like this way. Everything to the left of the staircase is what type of element? Tell your partner. Everything to the left of the staircase is a metal. Except who? Except hydrogen, yeah. Okay, hydrogen is a non-metal. Everything to the right of the staircase, those are nonmetals. I've run out of room. Non-metals. Okay. Now, what about these things down at the bottom of the periodic table? Yes. I could be asking for a group name. I could be asking for what type of element. You can tell me anything you want to about them. Yeah, we take off the UM. So we have lanthan. Those are our lanthanides. And this row here, we take off the and we have the actinides. Are these guys metals or are they non-metals? They are metals. Yes, Jonah. They are our inner transition metals, yes. You guys remembered a lot. Okay. Now, when you get a periodic table for a quiz or a test, it will be blank. It will not have the staircase drawn. It will not have anything labeled on it. Okay, I'm going to give you a blank one. So you need to know stuff. What? No, no, no. It's just going to look like this without all the writing on it. But it's going to have like iron, Fe26. You need to know the name like alkali metals. You need to know how to draw the staircase in yourself. But all of like this business, Cu, copper, 29, all that's going to be there. No, no, not blank. Sorry. That would be scary. You know, like, I have to fill it in. No. Yes. Yes, you'll definitely have the back as well. Okay. So you'll have the front, you'll have the back, you just won't have all the drawings and labelings, the extra stuff on there, okay? Now, let's go back to getting to know the period. Oh, yes. Do you guys remember what the main group elements are? The main group elements. Let's go back to our periodic table, sorry. If I was to color my main group elements in green, where would they be? Tell your partner. Tell your partner. Now, if you put up your hand, this is no guarantee you know it, but how many people think they probably know at this point? I got about half of you, okay? Half of you, that's pretty good. The main group elements are the ones that are most commonly used, and they're really easy to predict how they behave. And it is groups number what? 1 and 2. And then what else? 13 to 18. So all the way over to here. So those ones that I've just shaded in green, those are your main group elements. It's all the things in the main body except for the transition metals. So it's all the elements in the main body of the periodic table except for the transition metals. Is good? Okay, cool. I think we should watch some Tyler today. Yeah? Bill Nye is like loud and jump around and flash flash and hard to follow. Yes. So if you like Bill Nye, you can watch him on your own time, but not in my class because he drives me crazy. Okay, where did we get to? We were here. I don't want to be there. I want to be here. No, I don't. I want to be 2.2a. There it is. We are on page 78. Page 78. Yes, you can. 5 minutes? Does that sound reasonable? Okay, then you can't go to the washroom. Even with the lineup, you should be in and out of there in 5 minutes. Okay. Okay, so we're on page 78, and Tyler is going to look at, yes. Pardon me? Yeah. Okay, here we go. Let's get this video going. Wake up, little video. Here we go.
Let's take a closer look at atoms. Atoms are...
Pardon me? Yes, I'll hit the lights. And what was I saying? You probably know a lot of this already, but to have it all in context. Okay.
are the building blocks that make up everything. All stuff, everywhere. Here I've got some drawings. This is table salt, a solid. Here's water, a liquid. And finally, oxygen gas.
Okay, so we got table salt. And you'll notice he's written a symbol here for it. You'll notice it's capital N, little a, capital C, little L. So what does that tell you that table salt is made of? Tell your partner. See if you can remember what Na is and what Cl is. So we have Na. Who is Na? Na is sodium. Cl is chloride. It's actually chlorine, but when we put it together with another element, we call it chloride. Okay? And the reason Na is Na and not SO for sodium is that the Latin name for sodium is natrium. Okay? Now we have water, H2O. How many H's? Actually, I should.
And
H's are in every H2O. The black ones are H's. So we got 2 hydrogens. That's why it says H2. And then we have an O. And when you breathe oxygen, you're not just breathing an oxygen atom, you're breathing little pairs. Oxygen in nature always comes paired up with 2 oxygen atoms stuck together. Okay, O2. What model is Tyler using here? What model of the atom? Tell your partner, what model of the atom is Tyler using? What's he using? Billiard ball model. Who did that? John Dalton. Why is he using such an outdated model of the atom? Yes. Easy to draw, easy to understand. You don't have it overly complicated with things you don't need to see at this particular time.
What we're looking at here is what we'd see if we could take these 3 things and zoom in zillions and zillions and zillions of times. And if we could look at these closely enough, we'd be able to see that atoms, these little building blocks that make everything up. Now, atoms aren't really little colored circles, but it's a good way to think about them, and it's the way we'll usually draw them when we're learning about this stuff. Atoms are super tiny. They are so tiny, it can be really hard to wrap your head around how tiny they are. Here is something that might help you think about this. Take a piece of paper. Look at how wide it is here. All right? This is so incredibly thin. Now.
Okay, everyone, you're looking at a piece of paper, edge on. You can just take your paper and go like this. Look at the edge of it and think about how thin that is. Yeah?
Atoms are so small that it would take 1 million atoms lined up next to each other in a row to be as thick as this tiny width of paper.
So, if you stacked up atoms one on top of the other, how many would it take to be as thick as a single sheet of paper? 1 million. 1 million. Okay, so that's so many. Yes? It's almost impossible to imagine something that small. It's crazy. Crazy.
That's how small atoms are. Now.
Sorry, Jonah, yes. Oh, it actually is more than 2 atoms. We just drew that in to draw how many atoms it is. Yeah. Yes. Yes.
What I want to do now is look even closer at an atom. Let's take one of these atoms here and zoom in even more so we can see what's inside of it.
Okay, so before we do that, let's go through and make sure we've filled in the blanks on page 78. Atoms are the B for all matter. Atoms are the building blocks for all matter. Atoms are the building blocks for all matter. Atoms are super tiny. It would take how many atoms? 1 million atoms lined up to be as thick as this piece of paper. So if we're zooming even more, atoms are the what for all stuff? They are the building blocks. So it says, let's zoom in even more. Atoms are the building blocks, thank you very much, for all stuff. But an atom has an even smaller, and let's find out what it says next.
Here's a magnified view of one atom. It's not a perfect representation of exactly what an atom would look like, but it's close enough for right now. And check this out. The atom itself is made up of even smaller things. Right, so that we said atoms are like the building block for all stuff. But then if you look at an atom, it has even smaller building blocks that make it up.
So the atom has even smaller building blocks that make it up. And let's see if you can remember what those building blocks are before Tyler tells us. So what are these little black dots? Yes, those are the electrons. What is this area called? That is the nucleus. And what is it made of? Tell your partner, what is the nucleus made of? It is made of protons and neutrons.
So in the center of the atom is something called the nucleus. And the nucleus is made up of two tiny particles. There are protons, which I've drawn as red circles here, and then there are neutrons, which I've drawn as blue circles.
You can label whichever one you want, doesn't matter.
And then on the outside of the atom, there are these little black circles that I'm using to represent electrons. The electrons, you'll see, are connected to these sort of oval paths, and I've drawn these in to show that the electrons are constantly moving. They're flying around the outside of the atom at an incredibly high speed, whereas the nucleus stays solid here, right in the middle of the atom. Now, electric charge is very important when we're talking about atoms for a number of reasons. Protons.
So we're going to flip the page. Okay, so we're on page 79 if you're not already. Okay, 79. And there's little brackets after, we've drawn in some brackets here, bracket here, bracket here. Tell your partner what you think is going to go in that little bracket. Tyler was just talking about electrical charge. So see if you can figure out what's going to go in those little brackets. Tyler was just talking about electrical charge. Are we ready?
Protons have a positive charge. A proton has a charge of 1+. Electrons, on the other hand, have a negative charge. One electron has a charge of 1-. Now, neutrons, they don't have an electric charge at all. They have a charge of 0. And neutral is a word that we use to refer to something that doesn't have a charge. So neutrons sounds a lot like neutral. Now, positive and negative charges attract. Remember that opposite charges attract. And that has important consequences for how this atom works. We said that these electrons are flying around the outside of the atom. They're moving really fast. So why don't they just fly out into space? Well, the reason why is because the negatively charged electrons are attracted to the positively charged protons. So the protons kind of pull the electrons in. They keep them from just flying away. But the electrons are moving around so fast that they're not able to actually pull in here and actually touch the protons. So that's why they keep staying on the outside and don't just crash in here and all touch the protons. Now sometimes people ask, well, neutrons don't have a charge. Why are they important at all? Well, it seems that neutrons help keep all of the particles in the nucleus strongly connected.
That needs something to glue the protons together. The neutrons kind of act like glue. Chat with your partner. Why do we need something to kind of glue those protons together? Joanne, you said you had an answer. Am I correct? Did you have your hand up earlier? Yeah? Would you like to tell us? Okay, cool. Yeah, protons are positive and positive and they repel each other. Absolutely. So in order to keep them together, we need neutrons. And they have another force. It's not an electrical force. It's called a strong nuclear force. And it is stronger than an electrical force. And so it holds them together, even though the electrical force is trying to push those protons apart. Okay?
Now, electrical charge is important. Something else that's important with atoms is what their mass is, how much they weigh. So in order to figure that out, we have to look at the mass of the various things that make up the unit. Now, a proton and a neutron are very, very similar in size and in mass.
So you're going to fill out the first box, the mass of one proton or neutron. And the reason we say both is because they're very, very similar in their mass. They essentially weigh the same as each other. How many grams does one proton weigh? You see that number there on your page? 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 No. So they came up with another unit that is much, much smaller than a gram. Let's find out what it is.
And they both weigh about this many grams. Look at what a tiny number this is, right? There's a decimal place all the way over here. This is a number that it's best to represent in scientific notation instead. But however you write this, it's a really tiny, unwieldy number. So scientists came up with another way to measure the mass of a proton or neutron, and that's using a unit called the AMU, the atomic mass unit.
Okay, so I'm going to let you fill that in that box on the right. 1 AMU, which is one atomic mass unit. Isn't that a nicer number? 1. Better than 1.67 times 10 to the negative 24. Yeah, 1 is nice. So if I had a hydrogen nucleus and it had one proton and one neutron, what would a hydrogen nucleus weigh? 2 AMU. What if I had a hydrogen nucleus that just had one proton and no neutron? What would it weigh? 1 AMU. And actually there's two different versions of hydrogen. One that has just a proton, one that has a proton and a neutron. So some versions of hydrogen, their nucleus weighs 1. Other versions of hydrogen, their nucleus weighs 2. And in fact, there's a third version, and I'm running out of hands, so I'm going to need to make my head the second neutron. It has a mass of 3. Neutron, neutron, proton. Okay, I know this one is not the same size as the other one, but anyway.
And they said, okay, one proton or one neutron weighs about 1 AMU. That's a lot easier to use than this measurement here. So proton or neutron weighs about 1 AMU. An electron, on the other hand, is much, much, much smaller than a proton or neutron. It weighs only 0.0000549 AMU. So a tiny fraction.
So, in the sentence, it says an electron weighs a tiny fraction. An electron weighs a tiny fraction of how much a proton or neutron weighs. So we usually don't even worry about the electrons at all. Can you imagine if I stepped on the scale in the morning, stepped on the scale, and I'm like, oh, I still have my earrings in. Maybe I should take my earrings out because that will affect how much I weigh. Does that seem likely? No. I can leave my earrings in, I can leave my earrings out because the mass of these earrings is insignificant compared to my overall mass. Just like in an atom, the proton and neutron weigh about 2,000 times as much as an electron. So the electron is just so small in comparison, we just ignore it. So if I have a hydrogen atom with my one proton, and it's got one little electron zipping around the outside, how much does it weigh? One proton and one electron. Yes. Yes, but we're just going to say 1. Okay, we're going to ignore the 0.000549. We're just going to say it weighs 1. Okay, and that hydrogen atom that has 2, it has 1 proton and 1 neutron and 1 electron zipping around the outside. What's its mass? 2. Okay, we ignore the electrons altogether.
Of how much a proton or a neutron weighs. For this reason, when we're talking about the mass of atoms, which we'll talk about later on, we usually add up the protons and neutrons to find out how many AMUs the atom weighs. And then we usually don't even worry about the electrons at all because they're so tiny. They don't really have much of an influence on how much an atom weighs.
So when you get to the end, it says those things are just so tiny, we can just ignore their mass. So that's the last sentence of that paragraph. Those things are just so, the ring or the necklace, those are so tiny, we can just ignore their mass.
It's like when you get on a scale to weigh yourself, you don't worry about the ring you're wearing or whether you're wearing a necklace or something, because those things are just so tiny, they weigh so little compared to how much you weigh that it doesn't really influence your weight. So, protons and neutrons, 1 AMU, and electrons, a tiny fraction of that. Now, I said that the atom, the way it's drawn here, isn't a perfect representation of what atoms would actually look like. We'll talk more about that later, but there are 2 things that I want to bring up for you. The first is the electrons and how they move. This drawing might make you think that the electrons are spinning around in nice circles on the outside of the atom.
Is that what they really do? No, what do they really do? Tell your partner, what do those electrons really do? Yes, yes. They buzz around like hyperactive flies.
That's actually not what happens. They're buzzing around much more randomly, kind of like hyperactive flies all over the place. We'll talk more about that later. The second thing has to do with the size of the nucleus and how far the electrons are from it. If this were a real atom blown up many, many times, and the nucleus were the size of a grape, the electrons out here would be almost a mile away.
So if the nucleus were the size of a grape, so you're going to fill that in where it says 2. If the nucleus were the size of a grape, the electrons would make a cloud that reached about a mile away. I want you to hold your fingers up to about the size of a grape. Okay? And then think about a mile, or like 1.5 kilometers, if you feel more comfortable with that. Okay, because 1.6 kilometers is a mile. Tyler's American, so he uses miles. Think about how far that is. Do you ever run that far in PE or something like that? Like 1.5 kilometers? No? Should be. Oh my God, even I can run 1.5 kilometers. Not well, but I can. You guys are young. So that's how far far the electrons are from the nucleus if the nucleus is this big, which goes to show you how tiny the nucleus is compared with how big the atom is. So the atom is like zooming around, like it's over there, or the electron is zooming around, it's over there, it's a mile away, right? Or actually, half a mile that direction, half a mile that direction. Crazy, yes?
Just have this grape-sized nucleus, and a mile away would be the electron spinning on the outside. So that means that most of an atom is actually empty space. Anyway, now that we've talked about...
So that's our last blank. Most of the atom is actually empty space. Because if you imagine, here's the grape, and if the electron is a kilometer away that way, what's in between? Empty space. Yes? Because there's only like, you know, in a small atom, there's only 2 or 3 electrons, right? Larger atoms have a lot more electrons, but still, in a mile, they take up no space at all.
About what an atom looks like and the particles that make it up. We can go discuss some of the characteristics that we can use to describe atoms. These are things like atomic number, mass number, and net charge.
Okay. So,
here's a diagram.
We are done.
It's not perfectly accurate.
Your homework, which I'll give you a little time to work on right now, is to do pages 80, read 81 and 82 and 83. Do 83. Let me write this down for you. So we have page, whoops, 80, 81, actually 80 to 80, what was it, 80 to 83. And also, pages 72 and 73. You're going to read and do the questions. Yes. Most of 72 and 73 is review, but there are some specific properties of metals and nonmetals that you're going to read about. We will talk about them next day, and maybe we'll get out some samples so you can look at them.